Hello, everyone. My name is Akash Kamalesh, and as Vivek sir introduced, I am in Chat as a researcher. Uh, Extremely sorry for my voice. I have a bad cold, but yeah, I'll be presenting a mixture of experts today. That is, understanding how this concept works and why it works. So let's get started. The agenda for today is we will talk about what mixture of experts is, some background as to why it was even introduced, and do a comparative study of mixture of experts with traditional model training. And we will also understand the working method of a mixture of experts along with Mixtral. And the code demo is I that it's not feasible to run on a single collab GPU because of the number of 7 billion models that you would have to run parallelly, but I have the notebooks and I can share them with you. If you have compute resources available, you can definitely run it. So let's start off with the first main question that you would have. What is the mixture of experts, right? So the mixture of experts is like in the sense of the word itself or is the phrase itself. It is a group of different models. So it was it's a very old concept actually. It was introduced in 1994, and it was not introduced for NLP specifically. It was just introduced as a concept. So it was inspired of ensemble learning. That was a very popular bootstrapping method of training multiple models together to do the same task or different tasks. So, Mixture of Experts was proposed back in 94, and it's basically talking about splitting a base model into n parallel models. So, what that means is you have a huge model, and you would split that into n models that are running in parallel. Now, it's more of, you can also think of it as using n models independently together in parallel rather than splitting it. Both ways are correct ways of understanding. So in the context of a transformer, mixture of experts have two elements. So if you are familiar with the transformer architecture, you will notice that on the left side here, there is an input X going through the self-attention layer first, and then an add and normalize layer. But there's a difference here. It's usually a feed forward like layer that's after the add and normalize. But here there's something called a switching feed forward neural network. So this is actually a variant of mixture of experts called switch transformers, which we'll come to in a while. But essentially what happens here is that instead of sending the outputs from the normalized layer directly to a feed forward neural network, we would send it to a switching layer which has a router. So this router, if you see on the right hand side, it outputs a probability distribution as to which expert or which model to send the token to. So it goes at a token level. So you can see X1 and X2 are two different tokens, probably of a sentence, more parameters. So each of them are encoded and they're embedded. And after going to the router, they go to different feed forward neural networks. So P is equal to 0.65 or more to go to FFN2, and router, the second token goes to FFN1. FFN2 is nothing but a 7 billion parameter model that's running. So when you say Mixtral 8x7b, you have your FFN1 is one 7b, or FFN2 is one more 7b, or FFN3 is another 7 billion model, like that. So after that, you get your output, and it's you get your final output, and you calculate the loss for each token. Now, this is basically the entire setup that happens. And for every single layer of the transformer block, you do this. So the two components are that there is something called a sparse mixture of expert layer instead of a dense feed-forward network layer. You will be talking about this in the next few slides. So MoE layers have a certain number of experts. In example 8, in the case of 8x7b, each expert is a neural network. So the thing to understand, remember here, is that each expert is still dense. The mixture of expert layer is sparse. So yeah, we'll be talking about that. And the second part is a gating network or a router, which determines which tokens are sent to which expert. So this router is what is determining where to send the tokens. It doesn't send it to like all of the networks. You can choose if you want to send it to two networks as well and maybe take the concatenation of the outputs. But in this case, it goes to one. So coming to the introduction, the scale of a model is one of the most important parameters for better quality. And I think we've seen that when we've compared right from BERT to GPT to GPT-2 to GPT-3. And we've also seen cases where smaller models have performed better, like Llama 2 13 billion, etc. Those are different, but we're talking about in general, the scale of a model is an important parameter. So given a fixed computing budget, right? Training a larger model for fewer steps is better than training a smaller model for more steps. That is empirically found to be true. Mixture of experts enables models to be trained with far less compute. And the key word here is compute, not time, which because we will be talking about that later. Far less compute is how your mixture of experts benefits you. And dramatically scale up the model or dataset size with the same compute budget as a dense model. What that means is it would be like if I had, you know, if I made a big model that had 4 7 billion parameter models in one model itself. It's they say that scaling up the model with the same compute budget as a dense model is that it would take the same amount of cost to train these four in parallel rather than training it in one single, dense model. And the MoE model achieves the same quality as the dense counterpart. I mean, if this is not achieved, then there's no real point of using the mixture of experts, right? You would just rather train a large model rather than splitting into different parts. So the idea was similar to ensemble methods. It was to have a supervised procedure for a system composed of separate networks, each handling a different subset of the training cases. So this is basically like a fancier way of saying I have different models tasked to work on different tasks. So trained to work on different tasks. Sorry. So like if you had one more, for example, you could have one model for doing summarization of text, and you could have another model which was specifically trained to handle code-based inputs, rather than having one entire model that does both of them. So you would have an expert which has been like learned very well on understanding code, etc. And the other one would be very good at summarization or question answering. So this is essentially what mixture of experts talks about. Each separate network specializes in a different region of the input space. And yeah, so again, the main part that determines the weights is the gating network or the router. Now, during training, something to remember is keep in mind here is that the router along with the experts are trained. So the reason is, if you go back here, you see that the router is outputting a probability distribution, right? But how does it know the probability distribution? It can do that only when it's trained along with the models internally. So when you're training this model, you're training the router along with each of the experts together. So that's a very important point to keep in mind. Coming to why mixture of experts, dense networks have large neurons, right? So if you were to take GPT-3, for example, of around like I think 165 billion parameters, that's a lot of neurons in like all the weight matrices together. And in that also, whenever you give an input, it's not necessary that all the neurons are activated, right? Like there's only a certain subset of neurons that get activated based on your input. This is essentially what MoE bases off. They say that traditional LMs use all neurons in all the matrices for the forward pass. So when you give an input, it goes to the entire model, right? and then it comes out, which can significantly slow down inference time because as you scale up, your inference time will reduce. So a smaller set of neurons actually contribute to the output based on your given input. So it's not that, like, if I say give me code, certain neurons get activated than other neurons in the weight matrices, right? So this is why they've mentioned that having a dense network, having large number of neurons, is not really a good case for scaling up. And also, cloud-based opportunities from a business point of view, it has iterative approaches to corporate strategy. Why? Because you could have like, you could have your business solution, but for different branches of your, your business. So you could have different models trained on different parts of your business and running in parallel. So if you see on the left, this is a very simple diagram of how this would look. So if you have 8 different experts, the router would, for this case, is highlighting expert number 7 based on the input token that was given to it. Are there any questions as of now?
No, I mean, which neurons get activated and who manages that activation? How does that work?
So that is basically from training itself. So if you take a CNN also, like a normal neural network, when you train it, you are training it using, forward propagation, back propagation, using some activation functions. So when you're training it, there are the input from one neuron goes to all other neurons. Then after the activation function, certain neurons get more activated, certain neurons don't get activated to the next layer, right? So that is again by training itself. That is normal model training. So here in this case, as it's trained, it will understand that the router has to send this token to this expert, and the other experts won't be used at that time. And how that happens, I'll talk about in the next slide. But that's basically like it's the same as a normal model training, where when you send an input, it goes to the all the neurons in the first part. Then from there, based on the activation outputs, it goes to a certain neurons in the next layer, like that.
So are you saying the router is the key differentiator,
Yes,
right?
the router is the key differentiator here.
Okay, because in a normal neural network, different neurons get activated automatically. It figures out which neurons get
Exactly.
activated. But here you are saying you are doing a router-based management as well,
Yes, that is what your normal neural network is nothing but a dense network.
right?
Right. So, yeah, any other questions? Okay, no questions as of now. Coming to how that works is sparsity. So a sparsity is nothing but having a large number of zeros in your matrix, right? So if you look at, so this is an example of a sparse matrix. You have a lot of zeros, and pretty much your diagonal elements and maybe its neighbors are, numbered. So the sparsity is 74%. Now, how does this help? Think of it as a weight matrix from your dense network, right? If your model had such a weight matrix for a particular token, that is, so if you see that the computation is significantly reduced by so many orders, because if you had a dense matrix, a dense weight matrix, you would have small values in each of the zeros, right? It won't be completely zero. You would have small, like maybe 5, 2, in this case, like 5, 10, 15, 2, etc. So when you pass an input, it goes through every single what do you call it? It gets multiplied across every single row and every single column, right? But if you have a sparse matrix which understands that for a particular input only these neurons have to get activated, it saves so much computation because internally everything is happening through vectors, right? It's not happening through individual element multiplication. So when you do vectorization, it really increases the inference speed, because I would not have to look at the other zeros in the first column or the other zeros in the first row. I would just look at 11 and 22 and say, okay, this is where it has to go. So that is a sparse matrix, and that is what your MoE pretty much deals with. So Sparsity uses the idea of conditional computation. Conditional computation here is based on the input. So while in dense models, all the parameters are used for all the inputs, sparsity allows us to run only some parts of the whole system based on your input. So this helps in reducing the number of neurons that are being used. And again, this helps in the compute requirement. But to keep in mind, one thing is that this is only during your training and inference times. Because if you were to think about it, this does not reduce your GPU VRAM. It's still a huge matrix, right? Like you still have your matrix. It's just that it's sparse. That's all. So to still load that matrix into memory, you need to have a big GPU. So the idea of conditional computation allows one to scale the size of the model without increasing the computation. Again, as I said before, if you had a big dense weight matrix and you had to do forward pass across that matrix, you would have to multiply or look at the activations across so many different layers before you get your output. Whereas here it would just like quickly go through each layer because it sees so many zeros are there for it. Okay, coming to
So
router, we will
one
talk.
question on
Yeah,
that: how does that computation understand there are which are zeros that doesn't need to be get multiplied?
right. So essentially, internally, what happens is during vectorization, right? So the model, the input first looks at the vector that's given to it. So like in this case, if it were to look at 11, the first column, it would see that there's 11, that there's a value greater than 0, and it would just go through that point and get itself multiplied there and skip the entire thing after that. So internally, that's how activations work. They get we usually like give small values to the activations. If you've noticed, when you train a neural network, the activations aren't completely zero sometimes, right? Because if it becomes zero, that means it's a dead neuron, or you won't get any outputs from it. So this is different in that sense. All this is saying is that when the router is being trained, it will understand that for that token, it has to go here only or here only. So that is it's like a penalizing term. Like it says that the others aren't considered at all. So when the input comes, it sees that only this is highlighted for it, and it goes there. And these are learned during training.
Okay, thank you.
Yeah.
It sounds like a load balancer, right? When we are running
Yes.
a web farm, so
Exactly.
the load balancer figures out which server can serve the client request. So in this case,
This
you are
is
adding some kind of a load balancer.
it is a load balancer, but we'll also talk about some problems with this kind of load balancing in the few slides after this.
Hmm.
So, what is a router? A router is nothing but a neural network again. It is a network which decides where your token should go at each step. And it does this by outputting a probability distribution. So, when I say probability distribution, the term that comes to everyone's mind is softmax, right? So, it outputs a probability distribution to decide which expert to send it to, and it is trained along with the experts simultaneously. So, this is like an overview. Um, if you have so this is like an overview of your setup. There are 8 different columns here, if you notice, separated by those dotted lines. And that is your, like in this case, if you were to consider, you could say, or take Mistral into account. Let's say you had 8 different 7 billion parameter models of Mistral running, and your input is coming to the router here. That is your circle, the first circle. And this circle is saying, okay, this after training, it says that, okay, it has to go to this expert, the seventh one, and then you get an output. Then from there, you do your loss is equal to actual token minus predicted token, and then you backpropagate it. But the difference here is that backpropagation is backpropagation not through just that weight matrix that you saw, but it's also through the input of the router. Why? Because the router also needs to be trained. The router needs to understand that for these kind of inputs, it has to go to this expert, right? Without training the router, it won't really understand or know or learn how to know which expert to send the token to. So your backpropagation is going through the expert's neurons itself, the model, and it's being propagated backwards along with the router. So it's a two-step back propagation here. Yeah, so as I said, it's the gradients are propagated backwards through the MoE weight matrix and the router's weight matrix. The router will learn to send different tokens to experts as they're trained over time. Coming to the benefit, I think there was a message in the chat. Okay, no problem. Yeah, so the coming to the benefit, the same dense weight matrix is maintained as I mentioned earlier, but during inference time, the router will go pick one of the experts to go through, and you will have one nth of the amount of compute compared to the original LM. Because as I said, you wouldn't have to do the forward pass through the entire matrix of weights, but you would rather just look at one part of it. So you would have one nth of the compute, or you can think of it as n times the throughput. And n here is your number of experts. So one of the main things that you can relate this to is GPT-4, because there was a lot of speculation saying that GPT-4 is a mixture of expert setup. The reason being, they say that GPT-4 has like a trillion parameters, right? But a trillion parameters doing inference so fast is not really feasible, or it doesn't really sound true, too good to be true. So the mixture of experts setup for GPT-4 is not yet confirmed, but it is a very big speculation, and it most probably is true. But they say that having n number of experts, n 220 billion parameter models running in parallel, which have been trained on like maybe different tasks, and the mixture of experts picks it and gives you the inputs. Yeah, Gemini 1.5 Pro has MoE running. So again, these models, MoE models are done to increase the scale of computation whenever you have a lot of data. And yeah, so coming back to the benefit, AI models with sparsely activated mixture of experts significantly reduce the computational cost of the LLM training. And language models can be decomposed into smaller, specialized experts, which focus on distinct aspects of the data. Coming to the training process, it involves training the individual experts and the router. Now, the key word that I said earlier was that the compute is reduced during training time, but the time is not reduced. Sadly, the training time is like it takes a lot more time to train, and that the reason being, if you have like so many experts lined up in parallel, right? Like let's say you're scaling up to like 15 experts or 20 experts running in parallel, it has to understand that you have to first of all have a large data set, and your router should be so versatile that it can go to the correct expert, right? Because if it goes to the wrong expert, you might just get a weird output at the end of it. So training a mixture of experts takes a lot of time, and yeah, it's a time intensive process. Apart from training time, there are three other challenges which are present, which is, as Vivek sir mentioned, that this acts as a load balancer, but there is load imbalance computation as well. And there's also the problem of handling dynamic routing. And there's one more thing called token dropping. We'll talk about all of these now. So your load balancer issue is basically this. If I were to like go back to this slide, right? So here, if I had an input, and let's say for some reason the router gets biased, okay, let's say it gets biased, and it finds that while training that all the tokens are being sent to this expert or this expert, so it's just constantly sending it to like these two experts most of the time, and one or two times to these experts, right? So what you'll end up with is a very poorly trained setup of six experts, but two strong experts, which otherwise could have been distributed properly. So you would have two experts essentially in the setup running everything, and you'd be wasting a lot of compute here. And that is what your load balancing issue is. And there's a way to solve it. This was what Google had proposed when they had proposed switch transformers. They said that they add some noise, right? So when you're training the model, you add noise to the after the router's prediction. So when you add noise, it doesn't zero out certain experts. Like it doesn't make them zero. It gives them like maybe a 20% or 30% just because of the noise, right? So when you add, so after the noise, you pick top K instead of picking just one. So top K is essential because, like if you see, why not just select the top expert? It's because if I select just one expert, I don't the model doesn't learn which why this expert was chosen. So if I were to take two experts or three experts, let's say, based on the probability distribution, it can understand that how far apart these experts were in terms of probability. Like if was it point 0.6, point 0.2, and point 0.2, or was it point 0.6, point 0.4, and point 0.2? So then it'll understand that there is some closeness from this expert to this expert. So this is essentially what the load balancing issue does, because it will help preventing poorly trained experts at the end of the training process, and along with top K routing. There's one more. The load balancing issue comes with one more problem called token dropping, and this is a very serious problem. You can think of it like this: like if you have a classroom, right, and if you have maybe 200 students, and you have like 10 teachers addressing the students' questions, right, for example, and each teacher is specialized in one subject, so like physics, chemistry, or something like that. Now, let's say most of the students' questions are belonging to physics and chemistry, and the other subjects, there are very few students. So, what's happening is that the teachers from physics and chemistry are engaging a lot with the students, right? And the other teachers are not, engaging a lot with the students. So, you can think of it like this as the experts not attending to most of the input, which is where your data set really matters. The kind of data you're using, the representation of different tasks that you've mentioned. And one more important point is like if you have just two teachers for physics and like chemistry, they can only handle like 10 students at a time, right? They can't handle all 200 at a time. What happens to the other students who are waiting in queue? They either like leave because it's taking too long, or they just go to like another teacher just to see if they can clarify that, right? It's a very normal process, right? All of us do that when we have to wait for a lot of time in a queue. We just leave, or else we'll see if we can come back later, right? This is exactly what token dropping is. So when you have a lot of input going to one expert, and if the expert cannot handle that input because it's processing another set of inputs, these tokens get dropped at that current, that current stage of input. So what I mean to say is that at like let's say at this time step, the inputs have come to this expert, but this expert is busy. These tokens get dropped and are carried forward to the next time step. So again, it goes in like a queue, and it has to make sure that these tokens are learned, right? Otherwise, if the tokens are not learned, then as you keep moving forward, the importance of those tokens is lost because the context is gone. So this is one major problem that used to come with the mixture of expert setup. And yeah, so the expert capacity is like a threshold of how many tokens which can be processed by one expert. And it's actually like a formula that's been given, and it's fixed. So when the mixture of experts was implemented, it was a fixed number per expert. uh, yeah, so why is it important? Because you will not know how many tokens will go to each expert ahead of time, right? So you will never know, like based on your data set, you can't just say that these many tokens will go to this expert, these many tokens will go to this expert. And we're talking about tokens here, not sentences or paragraphs. Each single token, we can't say that, right? So yeah, when we run inference, some experts will be triggered. At the same time, there are shared computations which is applied for all the tokens. I'll talk about that in a little bit. So this is your expert capacity formula, and your hyperparameter here is the capacity factor. So expert capacity is the number of tokens per batch that each expert can handle. The number of tokens each expert can handle divided by the number of experts. So it's sort of like a normalization here that's done, multiplied by the capacity factor. So it's usually a number between like 1 to 1.25. And that number 1 to 1.25 is significant because if I say 1, it means that all the experts have like a very uniform capacity of handling the data. But if I say 1.25, then that means that these experts have to be ready for some overflow that can happen. And in that case, instead of sending the tokens to the next time step, we send it to another expert itself. So that is how this token dropping problem was proposed and was solved by the switch transformers. Expert capacity is a fixed number of tokens that each expert can be assigned, and the extra tokens are dropped if the capacity exceeds. So they are not passed to any expert for computation, and the model relies on a residual connection to reintroduce it in the next step. That's what I said earlier,
So Akash, I am a little confused. I
right?
thought the relative positioning or contextual understanding of tokens was key to LLM understanding. Now, if you
Yes,
break tokens randomly and put them in separate neural layers, they are not being correlated. So, how will natural language understanding work if the tokens have been segregated or distributed across neurons and no longer working as correlation or a group? I
that's
thought the
correct.
whole point of transformer was group understanding in with
Correct,
respect to each
correct.
other.
Yeah, no, no, that's very valid. But one thing you have to understand is also that if you're again, see, it depends on how the model is trained, right? That's why this setup is very sensitive, I would say, because if it's trained well, then what will happen is for a given sentence, it'll understand, it'll look at the entire sentence and then send it to the same expert. So it will still build some context because there are the attention mechanisms and the embedding layers before it goes to the MoE, right? So each token is processed before that in the normal way, like a normal transformer. The only difference here is that if it's trained well, if the router is trained well, based on the previous outputs, that is from the encoding and embedding layers, it understands the context of that sentence and sends all the tokens that are related to it into the correct expert. So it's not just the MoE that's doing it on its own. There is information from the encoder and the embeddings.
Got it. Got it. Okay.
Yeah, Vishal has a question, I think. Yeah, Vishal.
Yes. Akash, help me understand one thing. Uh, when we are saying that number of token when you're exceeding, right?
Yeah,
And we are passing that number of token to other expert. But we discussed already about this. The expert is trained for other task. Let's for
correct.
suppose one expert is trained on summarization, other expert is trained on for suppose scoring, right? Sentiment scoring.
Right, right,
When
right.
you're passing this extra token, so this complete context will change, right? Because other token which has been passed to the other expert now, that will result a not a very clear understanding on the model, right? Help me understand this part now.
Yeah, yeah. I'll clarify that. So this method that was talked about, right? So I told you there's two ways of doing it. One is drop it and then propagate it to the next time step, but that was shown to be very bad. So here what happens is that it's using top K routing in this situation. So you would have like, let's say, for example, you're given like a sentence, right? You're giving tokens one at a time. And let's say like 8 out of 10 tokens went to the correct expert. But then now that exceed that because that filled its capacity. So what happens is you send these two to the expert, which is like the second highest in the probability distribution, right? So you send it to that expert, and then in the end, you'll take a combined sum, a weighted sum of the outputs from both the experts, if you understand what I mean. So your context is maintained based on expert one, along with the expert two output. Obviously, there's going to be some loss in accuracy because, as you mentioned, expert two is meant for a different task. But to maintain the fact that the tokens are processed and then combined later with the output of the first expert. So after that, again, it goes through its embedding layers, right, and its decoding step. So that at that time, the context is rebuilt into the sentence. So the MoE part here is so this entire token dropping problem here was just so that it gets accommodated and it doesn't get dropped from the sentence completely. I hope you understood now.
Yes, I understood that particular point. One follow-up question on this, Akash. For suppose when we set the probability distribution function, right, which assign the probability to each expert, And there is
Yeah,
expert capacity also associated with that, right? So when a prompt comes on a specific task comes, so the PD function will take care of like where to assign this, which
yeah,
expert to assign that, right? But
yeah.
then how the expert capacity is decided? Do we that is decided based on the frequency of the prompt which are coming from the users, or like because these are actually correlated, right, with each other now,
Yes, yes. Yes,
right?
yes. So, yeah, so like this is where your the data set matters also. Like if you have a very skewed data set which has one kind of task, like one kind of instruction, for example, then that expert will be like, again, as I said, it will be learned more. But then that's not necessarily a problem because let's say if you have two experts, then it might be a problem. Like if you have two tasks and you have two experts, there'll be a problem because it's just 1:1, right? But if you had like four experts, let's say, what will happen is the experts itself aren't configured to run as like this task or this task beforehand itself. So you could configure them as and say that this expert is meant for this, but internally it might learn something else differently. So what can happen is that out of four, it sees that one is full, and initially in the training, like in the initial training stages, it might have it'll send the data to another expert, and that expert might become complementary with your first expert. So like let me break that down. If you have two tasks and you have four experts, and you initially thought that one expert would be able to handle it, but it doesn't, then it will just pick another expert and learn that expert for this task again. So you would have two experts performing the same task in that case. So that's how it scales up to different experts. If you are able to understand that,
Okay, Akash, thank you very much.
yeah,
So essentially, it's a kind of a servant master paradigm, right? Or parent teacher paradigm, parent child paradigm. It
it's like
teacher
a
student.
student teacher paradigm.
Parent. So teacher is learning what students can do the task best. So
Yes,
redirect that task to that student, right?
the redirect that student to that teacher, sir. That is the router.
Hmm?
Redirect the student to that particular teacher. That's what it's doing.
Oh, no, I mean the teacher will direct the task to the student as per the expertise of the students.
Ah, okay, like that. Yeah, okay, yeah.
Yeah. So we have seen this, teacher-student paradigm in many AI algorithms over the years. So, so somewhat similar to that, right? So,
Yeah.
okay.
So yeah, and again, coming back to that, the capacity factor is an important hyperparameter here in that case. So you would ideally want it to be somewhere near 1.25 or 1 to 1.25. Exceeding 1.25 would create like again sparsity in terms of each expert, which is not good because you would have a very sparse expert learned, very huge expert with very sparse representations. So one more thing is the last point. There can be cases where the expert is not assigned enough tokens to fill the capacity itself. So like this is again like if your data is not like there's not a lot of tokens going to one expert, then it's what happens is the rest of the tokens are just padded. So just to maintain uniformity of the shapes internally when giving out the outputs. So you would have outputs of the same sizes. Okay, so yeah, this is again like a revision to the gating method. One method is the softmax, simple softmax that you would use for routing. So this is for how you would route the tokens basically. So if you have a simple softmax, you get a probability distribution and you could choose the router. But as I mentioned, these kind of situations will create bias towards learning to specific experts only. So what you would do is something called noisy top K gating, which is what I explained. You add noise and then you take the top K, so that the expert is like the router also understands why each expert is getting the token. So this is the revisiting the bias towards experts. Tokens can get strongly assigned to few experts, leaving out other experts. This is a big problem because you'll end up with a very strong model with small number of weights compared to a strong model that uses the benefit of all the experts. So the two methods that could be done to solve it is the first one is using the randomness, that is using the noise. Because if you use the noise, what will happen is if you look at the diagram on the left side, you see that the expert choice is like a one hot encoded vector, right? It's saying that very strongly it's predicting that it has to go to expert 7. But when you add some noise, it'll normalize that distribution a bit and make it point 0.1, point 0.2, point 0.1, and point 0.4 towards expert 7 at the end of the day. So it won't strongly assign the token to that particular expert. The other method that's not that sounds good but is not done in practice is adding a penalty for the wrong router choice. So what you could do here is like if I were to add noise, right? By mistake, the noise might have like it could be like a 0.51, 0.49 situation that could occur. So 0.51 predict the wrong expert when it should have gone to the 0.49 expert just because of the noise that was added. So in that case, what's happening is it's learning wrong, right? It's technically learning wrong. But so in that case, what they do is that you can have this modified loss function, which does actual minus predicted tokens along with a penalty for the wrong router choice. So this is a very supervised way of saying that, like internally it has to go to this router only, but it's not done in practice because the router itself doesn't know which token, which expert to go to. So it's a theoretical concept. Coming to some parameters. Oh wait, before I talk about this, I wanted to talk about token dropping once more. One more point. Sometimes what happens is that in while training mixture of experts, people consider token dropping as a form of regularization. So how because it's like a dropout. It works as a dropout here, where some tokens are randomly dropped, and like you could make your expert robust in trying to predict it. That is one concept that they proposed. Google DeepMind has proposed, but it again depends on how many tokens are dropped. Because if 60% of your tokens are dropped, it's not helping your case. So memory requirements. As I said, your GPU requirements will be the same. That is for loading the base model into memory. So if you were to use Mixtral by base model, what I mean here is not 7 billion parameters. It is 8x7b. And also one more thing to keep in mind is when I say 8x7b, it does not mean 56 billion parameters. Why? Because as I said, certain parameters are shared across all the layers, right? So those are your attention and your embedding layers. Those shared parameters don't contribute to the increase, right? The only increase here is your MoE. So that is why you would end up with not 56 billion, but approximately 44 billion parameters. So the VRAM requirements will be like you would need to have enough to load around 44 GB into memory. Then that is just for loading the model. Training it is another whole case. So you would need at minimum 80 GB of GPU just to train a mixture of experts. The two methods of training, that is
This
adding noise. Yeah.
Yeah, this Mixtral is from Mistral AI, right, of France.
Yes,
So,
yes.
so they call their LLM as Mixtral. So they always had this, mixture of expert from version one of Mistral LLM, or it was a recent phenomenon. And is Mistral AI the creator of, mixture of experts?
No, they are not the creator of Mixture of Experts. They have used Mixture of Experts for their Mixtral model.
Hmm.
And yeah, so they've used MoE concept for Mixtral. I said in the beginning that Mixture of Experts is a very old concept, actually.
Okay, okay,
It's not a new concept. It has
got
been
it.
done only for LLMs very recently.
Yeah, Mixtral 8x7b was published in January actually by Mistral AI, right? So
Right.
very new.
It's a new space that is being explored for LLMs, but
Mhm.
there's some other work that's also been done, that is switch transformers, that has been shown to solve those problems that MoE presents, like all those token dropping and dynamic load balancing, etc. So yeah, Yeah, so you need to have enough VRAM to hold a 47 billion model. And the two methods of training, which is adding noise to the router and penalizing the router, is an extra overhead for training. Training, it increases training time. And computation is reduced only during inference because it does not go through the entire weight matrix. It goes through just one expert, and that's like one eighth, right? So the computation will just reduce that time.
So Akash, that should mean when you're using the model, right? Like for suppose a fine-tuned model of MoE, if you're using in practice, so
Right.
that will not be so intensive.
It will not be intensive when you are inferencing, when you're doing inferencing on it. So yeah, when you're like asking questions to it, it will be fast. It won't be intensive. But
Okay.
you will need enough GPU to load the model at least.
Mm-hmm. Okay.
So
Okay.
yeah, you would need at least like maybe a 50 GB GPU to load it, and another maybe 3-4 GB just to like do inferencing.
Okay. Okay.
Yeah. So when do you implement MoE? When you have from a business point of view, you would do this when you are a very large business and you have a high volume of requests which represent a wide variety of tasks. So if you could do this like for the public, or you could do it internally in your business as well. So like if you have a very huge company with different departments, doing different tasks, right? Like you have different databases for different departments, right? So if you wanted like different models for your team to work on, connected with each other, you could use a mixture of expert setup there. And when you have large data sets and targeted to solving different problems, when you want more throughput and when you get faster inference speeds, and when the main point here is that you have massively large language models to scale up to trillions of parameters. I think the last point of discussion is switch transformers. Switch transformers is a relatively newer concept that has come out by Google, and they've taken a step beyond MOEs and have built upon their said that the MOEs struggle with training and fine tuning instabilities, and they dive deep into these topics and suggest improvements. So, contrary to the idea of using at least two experts, Switch Transformers uses a simplified single expert strategy. And the effects are the router computation is reduced, the batch size can be halved, and communication costs are reduced, quality is preserved. So, how this does it is we'll talk about it now in a very overview fashion. Yeah, so parallelism, Switch Transformers is based off parallelism. MOEs were based off sparsity, right? That was like a very introductory, that was a very big thing for MOEs. So along with sparsity, there's something called parallelism. Parallelism is that when you have different parts of your setup in different machines running together. So it's like a distributed setup here. So there's different kinds of parallelism. That is data parallelism, model and data, and expert parallelism. So expert parallelism was what Swiss Transformers has introduced. The others used to be there before as well. So if you see this parallelism talks about like data, the data parallelism is saying that the same weights are replicated across all the cores and data is partitioned across those cores. So if you it'll make a lot of sense here if you look at it this way. Data parallelism, think of it as each square as one machine, right? One GPU. So if you have 16 different GPUs or 16 different cores, your data parallelism, the first diagram is talking about how each, like each block is each expert. So each expert is receiving the same data. And let's say you had one data point here and you pass that to each expert. And that goes only to these four experts, let's say, because of top K routing. What happens is that when you're backpropagating and when you're learning and you're training, it has to go through here and come back through each of these four. So each data point is sent to each of those four models, and you have to learn a combined representation of all of them. So this is like data parallelism. Model parallelism is basically saying that you have different parts of the model distributed across different, the setup, the cores here, and you can do a mix of both. That is model and data parallelism. It would give you different parts of the data to different parts of the uh, model here, and then you would combine them and have a learned representation. So there's a lot of like permutations here to talk about, but the main thing is expert and data parallelism here. Expert and data parallelism is these individual like squares you see are different experts, and that's why they're in different colors because each color is doing a different task. So each of these experts will receive the desired data. So the blue color data point would come to blue, the green color data point would come to green, etc. And this is what helps increase the reduce the computational requirements by a large margin, along with increasing the training decreasing the training time. There's another extreme called expert model and data parallelism. However, this sort of paradigm is not explored and done practically because it's too much of distribution. You're distributing the experts' weights, you're distributing the model across different cores, and you're distributing the data points across each. You're sharding the data to each part of the model separately. So propagating, you have to propagate through each part of the model, along with each part of the data, along with each part of the expert. So that increases the training time exponentially. However, it does lead to very high parallelism. So yeah, that's pretty much it.
Yeah, that last slide was quite interesting. Nice. It
Yeah,
shows
it's
how the parallelism concept works in various combinations or permutations.
yes, and different these methods have been done like they're in practice also. How you run a distributed LLM training setup, etc. But the expert in data parallelism was what switch transformers had proposed, and it
But
does.
what Akash? What about the quantization or model compression techniques? So they were also achieving LLM fast performance, right? So or
Quantization is it's doable, but I mean, there's nothing raw stopping you from quantizing your models and doing it. It's just that this setup is talking about if you were to use the original weights without any quantization,
Mhm.
and you can't train a quantized model directly. You need to add some trainable parameters to it, which is why you
So
have
like we
LoRa.
have a fine tuning with Q LoRa, quantized LoRa, right? So
Yeah.
so those were also model optimization or compression techniques.
Yes. Yes.
This is also achieving model performance improvement. So they
Yes.
are all trying to achieve similar goals, I guess.
Yes, they are all basically trying to reduce the compute required during training, but
Hmm.
this one does it in a very different way. So it
Hmm.
targets the expert directly rather
And
than passing it through.
your research suggests this is state of the art for new LLM versions like GPT-4 or Mistral LLM.
It's not, I wouldn't say state of the art because it comes with a lot of trade-offs. It comes with a
Hmm.
lot of trade-offs, to be honest. But
Hmm.
the only reason you would use it is when you want to scale up to a very, very huge setup. So it's
Hmm.
not something that everybody would do on a daily basis. It's just a research concept, or a very huge organization would try to experiment with this.
Right.
So yeah,
I mean, how does this method? I know this is mainly for training. When you go into the inference, where
right.
the data get validated now, yeah, is it really working or not? And
Yeah.
is there any mechanism in the inference where we are not finding these, the results are not matching and all that, to hold back to, do the training again or do something on this MoE? Like, you do get the MoE for the training and get all the coefficients or parameters, and you go into inference, and then you started failing, drastically. Is there any mechanism to fall back and anything like that in the research?
Fall back is not really. that I don't think it's a concept either.
Mhm.
The only thing you can do is to ensure, I mean, while training, you ensure that you're evaluating the model also and at different time steps. So you keep evaluating the model at every, like, X steps. So you can see that the model is performing correctly or not. Because, yeah, and then the other thing is making sure you do your token dropping and load imbalancing properly. So those two steps should be able to handle your problems. And one more solution you can implement is not just using one router, you can use multiple routers if your setup is so big, so that multiple routers can learn better. It's like having multiple attention heads, right?
Mhm.
Multiple attention heads attend different parts of the input. So here, multiple routers would also understand, why the token should go to. No, it's more like this router can understand that this token goes to this expert, but the other router will say it goes to go to that expert. But there's like another router which will decide which router to go to as well. So that's called hierarchical mixture of experts. And again, that's only in research. It's not implemented yet.
I see.
But
Thank
your question of fallback is it's not been done yet. In fact, that's true for any model training, right? Like there's no real fallback mechanism. You have to correct the training process and train again.
Yeah, I was thinking about this. Nowadays, enterprise LLMs are coming in corporations where they are training on their own data and smaller ones, and how that's kind of MoE in that sense. They are more focusing on specific work and those kind of thing in the training side. But as they increase the data and come back, so it looks like they have to come back to full training again
Right.
occasionally and redo those. That's the only way. Yeah,
Yep.
makes sense. Thanks.
Okay.
Uh, I have a quick question. I'm sorry, I'm not able to raise my hand here.
Okay.
Can you hear me?
Yes, I can hear you.
Yeah. Great overview, Akash. Really, for non-experts like me, this is very useful. Uh,
Yeah.
I want to, I always like to draw an analogy to a real world situation. And so maybe if you can help me out, in Google Maps, when
Yeah.
you model a long distance, let's say you're going from Bangalore to Chennai, it's
Okay.
generally a 5 to 6 hour drive, and
Right.
it gives you the prediction of the drive time based on the status as of that time,
Yes.
right? Now, if I take your example here, could we think of, so ideally, there should be a drive time prediction model for every, let's say, 1 hour slot. By using
Okay.
your analogy, could you say that every square, every colored square that you were showing could be
Right.
thought in terms of a 1 hour model? And when you
Okay.
want to do the overall drive time, you're going to aggregate, let's say, 6 1 hour models to get to that point.
Okay, but no, I understood your question and I understand that. But here in that case, you would not be doing it this way. You would be using a sequence to sequence pipeline. So this is a like there's different ways of training it. There's something called causal language modeling. That is how you train models normally when the sequence of data is not very important. But in your case, when you're saying the sequence matters, so you consider the last 6 hours, right? Last six machines. So that is where your sequence to sequence pipeline will matter. It is doable and you could do it, but you would have to change your pipeline to sequence and ensure that the weights are being carried forward at every part.
Okay, thank you.
So it's kind of it's sort of makes sense, but I don't see it being used for that kind of a situation. That is like an entirely different like problem. What you said, it wouldn't be a mixture of expert setup, because a mixture of expert setup would treat each expert at the same time, right? It wouldn't look at one expert for this hour only.
Okay, understood. Thank you.
Yeah. Any other questions? Yes, sir. I think there's no questions for today.
So you said you have some inference demo or no demo today?
I don't have the inference demo sadly, but I can share two collab notebooks which talk about how you can train a switch transformers model on your data. The other one is using the other model. I mean, the other notebook is trying to implement just to inference the switch transformers on a GPU. So if you have a large GPU, you can go ahead and use that notebook, and it will be able to. You can talk to Mixtra Latex 7B directly. And there's also a website that has the hosted Mixtra Latex 7B. If you want, you can talk to that as well. It's a demo model. It's not yet to be used in production. But
This
if you just want to
Mixture
try,
7B, is it available in Hugging Face or AWS Bedrock?
I think it's there on Bedrock. I'm not sure, but it's there on Hugging Face. I'm not sure
Okay.
about AWS Bedrock.
Okay.
Yeah,
Okay. Yeah, please share those notebook links. You can put it in our AI Lab WhatsApp group
yeah,
for
definitely.
all members to access
I
it.
can send it here as well if you
Sure,
want.
sure.
Yes, I'm just sending it in a second.
So excellent presentation, folks. If you want to join our AI Lab, reach out to me. I've shared my number in the message here. We are an AI community-driven company, and we collaborate on research and development. We do foreign projects in Gen AI, and we are also making our Moonshot Gen AI product. So feel free to reach out if you're interested in collaborating. So any final questions for Akash here? You can see that we have some remarkable experts like Akash in our community. So it would be good to collaborate. Yeah, Hari, you have raised your hand. Yes, go ahead.
Hi Akash and Vivek.
Hello.
I would like to my doubt or a question is that is there any real world application currently emerged or came like based on this mixture of experts which they can able to benefit? If any other organization, is there any application that came up right now?
There's an implementation by an open source community. It's called Open MoE, and that is meant for handling. Again, it's an open source initiative that was based off switch transformers to just from a proof of concept perspective. But as a company, if you're asking me which company uses it, I'm not too sure. That's something I would have to look at. But internally, GPT-4 and Gemini do use mixture of experts because they say that these models have trillion parameters, and like it's absurd, right? You can't think of trillion parameter models running parallelly unless there is some mechanism like this. So yeah, I hope that answers your question.
Okay, yeah. Thanks for
So GPT-4 has not announced explicitly they are using mixture of experts, right, Akash?
No, they haven't explicitly announced it.
Unlike Mistral, which has said it is a mixture of experts, right? Their new model Mistral.
Yeah, they haven't explicitly said that.
No, was just Googling. I found that it says that the Mistral is mixture of experts model.
Yes, yeah.
So Mistral is not hiding that basically.
Mistral is more towards open sourcing rather than and research rather than commercializing because OpenAI has gone the commercializing route now.
Mm-hmm. What
Yeah.
about Llama? So is Llama also getting into mixture of experts, or you don't see that?
We're not too sure, but there is a lot of so there's something very interesting about Llama that they have reserved at least I think 100 or 1,000 or 10,000 H100s, NVIDIA H100s. So NVIDIA H100s are like the best GPUs in the world, and they've reserved 10,000 or 20,000 of them already. So you won't find them anywhere. And I think that's because they're training Llama 3 that's coming up.
Yeah, I believe Facebook has a big deal with the NVIDIA
Yeah, yeah.
for Llama research. Yes.
Yeah, I think you are right. About 10,000 plus part of it, they were working on it. But I think to look at all of these, as it goes beyond these few large people with trillions of dollars, they will have to come to some of these model eventually, and that will be the sweet spot for many corporations to go beyond it. Yeah. So,
Yeah. I think Llama is just like, because Llama 2 was released quite some time and they have been silent. So they are now releasing Llama 3. It might be again a mixture of expert setup, but no one's sure yet.
Mhm. Okay, any other questions, friends? Okay, with that, we come to the end of this. Thanks a lot, Akash. Fantastic presentation as always. And always excited to see and kind of look forward to whenever we announce your webinar, because your content is always marvelous. Thank you, audience, for joining. And do reach out to us if you want to collaborate with us. Thanks a lot, Akash. Thank you, audience.
Thank
Have a
you.
good rest of the weekend.
Thank you.